Okay, good morning, everyone. Before we get started, Rachel has something to share with everyone.
Cool. Hi everyone. You guys probably have been hearing about this or seeing posters around, but I just wanted to do a quick promo for the hackathon at the end of this week. It's going to be a Friday night networking event and then an all-day Saturday hacking event. It's a really great opportunity to build your resume, show your skills that you're able to work on a project in a smaller scale of time. I know that job interviews love to hear about hackathons. I've talked about previous ones I've gone to at interviews, and it's gone wonderfully. And so I really recommend taking a moment to consider doing this. It's a really great event. You'll meet local tech businesses as well, build connections, and then show them what you're capable of. So everyone, please consider it. There's a sign-up link over here if you want a QR code, scan it. Or if you look around innovation, there should be posters around that you will be able to scan as well. So thanks everyone for your time.
Awesome. Thanks, Rachel. Okay. Back to evolutionary robotics. We are working our way through the history of the field. We will probably finish that off today and dive into legged locomotion on Thursday. Undergrads, you are working on assignment. You're working on assignment 7 now. Graduate students, you've moved on to the second differentiable assignment. The TA is grading all of the first 10 assignments, and I will be grading the differentiable assignments. I am not as timely as the TA. I will do my best to tackle that. Hopefully, the differentiable assignments, you know when you've got it right, and you also know when you've not got it right. So hopefully, you know where you are, and you're carrying on to differentiable assignment 2. Any questions about the A's or the D's? Going once? Yes.
Like the video player in the differentiable assignments.
Yes.
It work. Is that just like, is it outdated or?
It is absolutely outdated, yes. So in the differentiable assignment, it generates an MP4 in the Colab, and then there's an attempt to download it.
Yeah.
If it's outdated, it's not working, you should be able to download it manually from Colab, but it's a pain in the butt. You can update the codec. If anybody figures out how to update it to a most recent version, send it to me, and I will embed a short video update into the tutorial. Thanks for that. Yep. Any other questions about the assignments? No? Okay, so we are going to finish off lecture 9 today on minimal cognition. Just as a reminder, since 1956, people have been arguing about what exactly intelligence is, how do we build it into machines, and if we do build it into machines, how do we know that it's there? Is ChatGPT intelligent or not? Does ChatGPT understand or not? Is ChatGPT sentient or not? Feel free to argue about it over beers. But ultimately, we want useful, safe, autonomous machines. So in the minimal cognition experiments, the investigators sided with Turing and decided, we're just going to try and make very, very simple machines, but they are going to act in a way that if you were to observe their behavior, most reasonable people would attribute some level of cognition to that agent. If that agent does X, it's kind of intelligent. If it does X and Y, it's probably intelligent. If it does X, Y, and Z and W, okay, it's getting increasingly difficult to distinguish it from us. That's the stance they take. Again, you may or may not agree with that view of things. That's the idea in the minimal cognition experiments. And in the minimal cognition paper that we've been investigating last time and today, they picked 4 building blocks of intelligence that most folks, at least in cognitive science, would sort of agree are necessary if you need to act intelligently in the real world. And we looked at the first of those 4 building blocks last time, which is the ability to detect affordances. This is the idea that when we look around our environment or a machine looks around its environment, we're not recognizing objects or distinguishing friend from foe and food from poison based on geometric properties of the color of things. We're reasoning about, in our heads, how we may or may not be able to interact with that object. What kinds of things does that object afford to me? What kinds of things can I do when I interact with that object? We were looking at a, not surprisingly, minimal agent. looking at a minimally complex set of objects, a pair of falling cubes, and the affordance here that we're going to evolve our robot to determine is whether or not the gap between the objects is wide enough for the robot to get through. It can't tell us whether it's perceiving that affordance correctly or not. It just shows us by either threading itself, getting into position so that the blocks fall on either side, if the gap is wide enough. If the gap is too narrow, the agent evolves to get out of the way. Okay, that's where we were last time. We looked at the most fit CTRNN, the best brain that evolved for this agent. And when you drop that evolved brain into this agent, it's a little bit of a fraidy cat. Most of the time, it'll run away if the aperture is too narrow. It will thread the gap if the gap is wide enough for it to get through. If it's not quite sure, it'll err on the side of caution and most of the time run away. Not an optimal thing to do. If the aperture is wide enough to get through, the agent should be going through that aperture every time, but it errs on the side of caution. Most humans, when they learn of this evolved behavior, in retrospect kind of nod their heads and say, that's probably what I would have done. If it was very, very close and there was a good likelihood that I would get hit, I would run away. You might argue that this agent is, in this simple setting, solving the alignment problem. We want machines that are not just safe and capable out there in the world, but that we want them to react to situations, especially uncertain or potentially dangerous situations. We want them to react in the way that we would if we were in their shoes. Boiling that down to a fitness function and evolving robots to do that, very, very tricky. In general, the alignment problem is unsolved in AI and robotics. We've got machines and computers out there that are exhibiting increasingly intelligent behavior, but they don't always do it in a way that's aligned with our values, our morals, our common sense, our better judgment, et cetera, et cetera. Okay. We ended, I think, last time by tackling this figure down here. Again, in this case, the researchers are still investigating this one single CTRNN that evolved for this agent. They took that evolved CTRNN and they dropped it back into the robot many times to investigate what that CTRNN caused the robot to do under different circumstances. In this particular analysis here, they dropped that CTRNN into the robot thousands of times, and the resulting behavior is represented by an individual pixel in this panel. So let's have a look at what's going on here. On the horizontal axis here, the label is initial horizontal position. So this is the initial horizontal position of the robot relative to the blocks when they start falling. So all of the pixels on the right-hand side here correspond to high positive horizontal position. That means the objects started falling above and to the left of the robot. All of the pixels on this side of the panel here, the initial pair of objects started to fall above and to the right of the robot. So far, so good? Okay. Vertical axis, relative aperture width. Sometimes that falling pair of objects were wide enough for the robot to get through it if the robot went between those pair of objects, and sometimes the aperture was too narrow for the robot to thread through it. So far, so good? So they're dropping the object pair from different horizontal positions at the top of the screen, and the aperture is either too wide or too narrow for the robot to get through. What does it do in all of those conditions? Most of the pixels here are white, representing for that initial horizontal position and that relative aperture width, the robot did the right thing. Whatever the right thing was supposed to be in those conditions, either run away or attempt to thread the needle. But not every pixel is white. What's happening? There are a few gray pixels and a few black pixels. Gray pixels indicate mediocre behavior. So this was the robot kind of not quite sure what it was supposed to do. Maybe it hit one of the objects. Poor black is it did the wrong thing. It ran away when it should have stayed, or it stayed when it should have run away? It's not white noise here. There's some pattern to the gray and black. What is that pattern telling you about this particular evolved CTRNN? It's not optimal. If it was optimal, this entire panel would be all white. What's happening? Idea?
Like at mid and extreme ranges, it does good, but at like a lower range and like a higher mid range, it does worse.
Okay, so in the upper half, it does worse. What does that mean, generally speaking?
I think like as the aperture gets wider, it becomes more uncertain.
So whatever it's doing wrong, it's certainly when the aperture is wider than the robot. That's the upper half of the panel. It's uncertain. So now we're going to start attributing cognitive states to the robot, which is perfectly fine. Bratenberg would be nodding his head saying that's what we tend to do. It's okay. We can argue about whether or not it's actually uncertain, but that's a philosophical discussion. We can see that it seems like it's acting as if it's uncertain. It doesn't always do the right thing. Can we be more specific? How is it failing when the aperture is too wide? There's some regions where it's doing particularly poorly. What are those regions, and why do you think it's performing particularly poorly under those conditions?
The apertures, we see around 2, so the robot should be standing in the middle, letting the blocks fall on either side of it, and it looks like when the initial horizontal positions are extreme.
Yep.
So in that case, it would mean the robot is moving towards the center at some point and then doesn't escape or doesn't stay there.
Could be. So sorry, you mentioned 2. Just a point of clarification. So the vertical axis is reporting relative aperture width. Sorry, I should have provided this detail. What does relative mean? It's relative to the agent. So 2 here indicates that the aperture width is 2 units wider than the robot. How much is 2 units? Trust me, it's a lot. The agent can easily get within this aperture and super easily within this aperture. What's going on at an aperture width around 0? Relative aperture width.
Are the blocks just connected at that?
They're not connected. What does a relative aperture width of 0 mean?
It's the same width as the robot.
Same width as the robot, right? So the robot could, in theory, if it was really, 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 really good, it could thread the needle. What is the robot doing when that gap is just about the same width as the robot?
Running away.
Right. The gap is 0 or a little bit above 0. It's running away. It should be going, but it's a fraidy cat, and it's doing, the black pixels say, the wrong thing. Poor behavior according to the performance metric or the fitness function that we evolved the robot for in the first place. On the other hand, as humans, we say, yeah, okay, but again, maybe a good thing to do. If you're unsure, get out of Dodge. Okay, you've mentioned these regions over here. What's going on here? Do you mind repeating your idea?
So it seems like when it starts at an extreme horizontal position, we should want it to be between the 2 blocks.
Possibly. Up here we do.
Yeah.
When the blocks are far to the left or far to the right initially of the robot and the aperture is too narrow, we want it to stay away.
And the gray would mean that it's not doing what it should, but it's also not doing the opposite, so it would be getting struck.
It's getting struck by the blocks. So the blocks are either far to the upper left of the robot or far to the upper right of the robot. And clearly it doesn't stay there because it's gray. It's getting hit. It's neither running away nor threading the gap. Why do you think there is this uncertainty here? Or behavior, physical action that looks like uncertainty? Why do you think that might be the case in these 2 regions?
Can the robot not see both blocks?
We discussed this last time. It's a good point. It's not really clear how long these infrared sensors are, how far they can sense. Maybe the robot just can't see the pair of objects for a while and is kind of wandering around and then sees it, but maybe it's too late. It doesn't have enough time to resolve, to detect the affordance. It's not sure what to do, and it gets hit. It's not clear from this data, but maybe that seems like a reasonable hypothesis, and we could go have a look. What about this black tower in the middle here? What is this? Let's start with the behavior. What is this denoting about the robot's behavior? And then we can hypothesize for why it's exhibiting that behavior. What does this tell you about the robot's behavior under these conditions?
It's doing the wrong thing.
It's doing the wrong thing, and what is the condition here that it's doing the wrong thing in?
It's just when the blocks start directly above it.
The blocks are right above it. Seems like kind of ideal conditions, right? The robot doesn't need to actually even go. In theory, it doesn't necessarily need to go anywhere. And yet, even when a pair of blocks is placed above the robot and the aperture is super wide, the robot runs away. What gives? Seems odd. This is a tricky one. Intuitively, it seems like this would be one of the easier cases, and yet it's not from the perspective of the robot. Ideas?
It kind of feels like the robot needs more context to understand that it's in the right spot.
Maybe. I mean, the robot's free to move. It might very well be brushing its whiskers along the underside of the objects. Who knows? This plot doesn't tell us whether the robot just stays immobilized. Maybe it doesn't have enough context, or it doesn't have the right kind of sensory information it needs to solve the problem. It's not clear. It could be running away and coming back again, running away, coming back again. Who knows what it's doing? All we know is that at the end, it ran away. Odd. This is the most fit controller that came from evolution. Remember, during evolution, every ctRNN, including this one, was evaluated num trials times. So it was evaluated multiple times under different conditions, different pairs of falling blocks. Why do you think this is happening? These kinds of things are what keep AI researchers and roboticists and autonomous vehicle developers up at night. This is the scary thing. We trained our machine, we evolved our machine, it's doing super, super well, we put it out in the field, and sometimes it does the wrong thing, even under conditions which to us seem like a no-brainer.
Maybe because its previous generations always got punished for just standing still, right? And so it's deciding to avoid regardless if there's a chance or not.
True, right. It does have this sort of bias, this particular ctRNN, based on maybe its parents' experiences and its grandparents' experiences, generally tends to run away, which is what you see down here. But that doesn't necessarily explain why, at this particular set of conditions, it's really doing the wrong thing.
That's the one condition where you have a perfectly symmetrical set of input, and so it would seem to indicate that the robot needs some asymmetry, that it's developed this brain, this neural net, and relies on that.
Could be, right? So if the blocks fall directly above the robot, the sensory information coming back from the gray line segments here is symmetric. And maybe it just doesn't have enough context, doesn't know what to do with that. Maybe during evolution, it mostly experienced things like this, non-symmetric sensory information. It's kind of hard to say. We don't really have enough data here. Maybe it just didn't see this condition during evolution. Remember here, they played back the ctRNN and they dropped the pair of objects from different horizontal positions above the robot. There isn't a line segment emanating at 0. in these experiments, this was analysis done after evolution, at least in this analysis, they never dropped the pair of objects from directly above the robot, which leads me, and I've read this paper now many times, leads me to guess that during evolution, among these number of trials that they performed on every evolving CTRNN, they never dropped the pair of objects from directly above the robot. It just never saw that situation during evolution. This is what scares AI folks and roboticists, is that you deploy an autonomous vehicle and it's going to experience some situation. Its camera is going to collect some frames for 5 or 10 seconds that are really weird, things it's never seen before. You've probably seen your own bloopers and blunders on YouTube. My favorite is there's an autonomous vehicle and it's driving behind a flatbed truck, and that flatbed truck is filled with a whole bunch of traffic lights. The Tesla car goes completely bananas, right? What are you supposed to do? There's traffic lights. I know I'm supposed to stop or go or slow down. There's 20 of them in front of me. None of them are flashing red, green, or yellow, which I haven't really seen that much in my training set. Who knows what the autonomous vehicle is going to do under those conditions that it never saw during training? No one, in my professional experience, no one has a good answer to that question yet. Okay. All right. We spent a lot of time on affordances. Let's move on to the second of the 4 cognitive building blocks that they tackled, which we've actually already seen before. Something that's kind of important to do if you want to get around in the real world is be able to know where you end and everything else begins. Where did we see a robot that was learning to discriminate between self and non-self? Baby bot, right? Said, oh, there's this blob. Whenever I send commands to my motors, suddenly there's a moving blob, and when I stop sending commands to my motors, that blob disappears. That sensor-motor relationship. I do something, and I see something as a response. That loop, that kind of data that I get back, I'm going to call that thing self. Self is not this geometric description. It's I do this, and there's this sensory repercussion. Okay, we've already seen a robot that does that. Here's a much simpler one. In this case, we're going to nail our little Space Invader robot to the bottom of the screen. It cannot move its body, but it has a little arm, and it's got a little clenched fist at the end of that arm. And this particular robot has one and only one motor that rotates its arm back and forth, causing its little fist to trace out this curved trajectory that you see here. Very, very simple. So we've got one motor neuron inside the CTRNN, one motor, and again, 1, 2, 3, 4, 5, 6, 7 proximity sensors. There are 7 sensor neurons inside the CTRNN. Why does this robot have a little clenched fist? Well, you'll notice that as its fist moves in front of its proximity sensors, that little fist can block the proximity sensors. Its own motion induces changes in its perception. In this case, these 7 proximity sensors. While it's waving its little fist back and forth and causing changes to its own incoming sensory information, there is also a falling object that's falling from the top of the screen. And in this case, this object can fall at various diagonal directions at various speeds. And you'll notice that this object also is being detected by the robot down here. So in this hypothetical situation at this moment in time, the robot's 7 sensors are reporting far away, really close, far away, far away, far away, kind of far away. That's the information that's coming in as 7 floating point numbers. There is nothing from the robot's perspective that tells it that this is self and this is something else. We talked about proximal perspective and distal perspective a few weeks back. You have a distal perspective on this robot. You're literally viewing it from a distance. You can obviously see this is the fist, and this is self, and this is non-self for that robot. This robot cannot necessarily tell the difference between these things. It might be easy at this moment in time because there's something really far away, and maybe the robot learns, okay, that's not me, I can't reach that far. It doesn't know any of that. All of these falling objects, whatever angle and whatever speed they fall at, they will eventually hit somewhere on this semicircular trajectory. They're all falling towards the robot. Given all of this lead up, you can probably guess what they're going to evolve this robot to do. As the object is falling, grab the object. That when this object, at whatever time step in the simulation, this object intersects this line, the fist should be there also. That's the task that they're going to evolve the robot to perform. So they're not actually going to evolve it to discriminate between self and non-self. They're going to evolve it for object capture. Grab the falling object. And in order to solve this task, the robot is going to have to discriminate between self and non-self. So far, so good? Okay, so let's go through evolution. Starts like before. They're going to evaluate a population of CTRNNs, and for each CTRNN in the evolving population, they're going to evaluate that CTRNN num trials times. For each of those trials, they're going to get back a value p sub I, which is the performance of that CTRNN during the ith trial. And they're going to evolve these CTRNNs to exhibit good behavior on average. Okay, what is p sub I? It's a little bit of an awkward equation, and there's a typo in this paper. It shouldn't be max, it should be min. You'll notice that p sub I is a function of only one variable on the right-hand side of the equal sign here, which is theta sub I. And theta sub I is the angular error at the end of the ith trial. So what's angular error? The angle is the clue here. So this object is going to hit at some angle relative to the agent on this trajectory here. So maybe the object hits over here, and my little fist was over here on the opposite side. That's high angular error. If the object hits over here and I rotated my little fist to be over here, there's no difference between these two angles, and angular error is 0. Tell me about this equation. What is evolution trying to do? What is evolution trying to get the CTRNNs to do in terms of angular error? The easiest way to reason about this is we now know what we want the robot to do. Make sure that your fist is where the object hits, which would be a theta sub I of 0. So you can plug theta sub I theta sub I equals 0 into the equation and start to work backwards. There was an idea here? Okay. If theta sub I is 0, what do we get for p sub I? We get 0, we're taking the minimum between pi over 4 and 0, which is 0. So we've got 0 over pi over 4, which is 0. And then? 1, it's a 1, right? So the best thing you can do, the best thing the CTRNN can cause the robot to do, we'll get a p sub I of 1. What if theta sub I is really large? You'll notice that there's it's an absolute here. So it doesn't really matter whether the fist is too far to the left or too far to the right. What is a high angular error set p sub I to?
0.
Pretty much 0, yeah. So p sub I is going to range between 0, the worst thing you can do, p sub I of 1, best thing you can do, and then we're going to average that over a whole bunch of object drops. Okay, evolution, 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 evolution. At the end, they get a CTRNN that scores pretty close to 1. Under most conditions, that evolved CTRN with the highest fitness causes the little fist to rotate and quote-unquote catch the object. Like before, the investigators are not showing us the evolutionary trajectory. They're just going to now analyze how does that one good CTRN do under a whole bunch of other new conditions, things that that CTRN may not have seen during evolution. Okay, what are all those conditions? On the horizontal axis here, they're plotting final object angle. This is where the object hits this dashed line relative to the robot. So minus pi sub 8 is the object hit just to the left of the robot. Positive pi over 8, the object hit to the right of the robot. A final object angle of 0, the object hit this line right in front of the robot. Vertical axis, final angle of the arm. Same thing. Minus pi sub 8, minus pi over 8, the arm was here. Positive pi over 8, the arm was here. 0, the arm was here. How does this CTRN do under all those different conditions? The object hits at different locations relative to the agent. What does it mean that all the black circles here are lined up more or less on the diagonal? What does that mean?
It means that it performed well.
It performed well, right? Most of the time, wherever the object hit, that's where the little fist happened to be. The robot caught the object most of the time. What do the vertical lines represent? We mentioned this last time.
Those are just error bars. So
These are error bars. So on average, if they do this a bunch of times, the little fist isn't always exactly where the object hits. It's a little bit to the left, a little bit to the right, but close enough.
Well, the fist itself has a radius.
The fist itself has a radius. I'm imagining the arm, it's the arm angle here. They're actually taking the angle of the arm to compute this. Question?
This might not have been a part of it, but is the size of the object like put into it? Like what part of the object is the angle taken from?
Oh, I think again, it's the center of the object. So the object, this big black circle, touches this line, and wherever it touches this line, that's final object angle.
But does the object hit the center of it or just any part of the object?
Good point. So there's no collision detection and resolution in this experiment. The fist can pass through the circle. Good observation. Okay, so looks good. Most of the time it's doing what it should do. Fine, okay. This one's a little tricky to parse, so we'll take this slow. Same thing, it's the same single best CTRN. They're gonna analyze it even further. Things kind of look good, but what exactly is going on here? You'll notice that there's a whole bunch of wavy trajectories here, and we're gonna start from the top and work our way to the bottom. You'll notice that one set of trajectories starts up here and to the left. The other set of trajectories starts upper right here. What does this mean over here? What does things to the left mean in this plot, and what do things to the right mean in this plot? Okay, what this means is that over here, angular position of -8, angular position of what? It's angular position of the arm at the moment that the object starts falling from the top of the screen. So in all of these trials here, they put the object at the top of the screen. They haven't even started the simulation yet, and they crank the robot's arm all the way to the left. So when they start the simulation, the object starts falling, the robot wakes up, meaning sensor values start flowing through the neural network to the single motor. At that point, the robot finds its initial arm angle is pi over 8 radians to the left. So far, so good? So they want to see how the robot does when it starts in different situations. All of these trajectories here correspond to experiments in which they initially cranked the robot's arm to the right, pi over 8 radians to the right. So far, so good? Okay. They did this a whole bunch of times, arms starting to the left, and a whole bunch of times, arms starting to the right. Then there is the color of the trajectory, or the grayscale of the trajectory. The trajectories are shaded according to the initial angular position of the object now. So dark colored trajectories correspond to objects that started falling minus pi over 8 radians above and to the right of the above and to the left of the robot. It's hard to see these dark trajectories because they're actually drawn underneath some of these light trajectories, but bear with me. There are some black trajectories starting here. What does that mean? There are trajectories that started to the left, which means the robot's arm was rotated pi over 8 radians to the left. And that trajectory is black, meaning the fist is actually occluding the robot's ability to see the object. The object is pi over 8 radians above and to the left of the robot. So far, so good? Okay, let's stay on the left of this figure. Let's take one of these light-colored trajectories. One of these light-colored trajectories is starting over here, which still means the arm is rotated to the left, pi over 8 radians to the left, but the color of the trajectory is light, and if we look at this color bar up here, very light colors represent to the object starting to fall from pi over 8 radians above and to the right of the robot. It's over there, and that object is not occluded by its own fist. Takes a little bit to digest that. Everybody understand a black trajectory starting over here and a light trajectory starting over here? Two different situations, same thing over here. Okay. All right, now that we understand these trajectories, hopefully, what does it mean as we descend along this figure? They've written time on the vertical axis here. You can probably guess. These are time in simulation time steps. The robot's arm is cranked to the left, and if we follow one of these light-colored trajectories, that's the object starting to fall above and to the right of the robot. And as we follow that light-colored trajectory down, that object is falling. And if we follow that light trajectory all the way to the bottom, the light trajectory ends right here, as do all the other trajectories. What does it mean that all the trajectories are ending in the center of this figure? Not to the left of the figure, not to the right of the center. All of these trajectories are converging at the bottom center of the figure. What does that mean? Remember I told you the trajectory itself, the horizontal points, the points that make up the trajectory, their horizontal positions indicates the angle of the arm. The trajectory starts far to the left, which means the arm is far to the left. This trajectory initially starts to go even further to the left. What does that tell you about what the robot is doing in this situation? Takes a bit to digest this figure. What is it telling you? What is the robot doing? No? The horizontal positions within the trajectory are representing the angle of the arm. The arm started far to the left, the arm goes even further to the left. And then the arm starts to come back towards center, but the arm stops before it ever gets to the center, and the arm goes to the left again, arm goes to the right, left, right. The arm is shaking back and forth above and to the left of the robot, and then at some point, The little arm crosses the midline and shakes a little bit over here, and then the arm comes back and ends pointing directly up. Should we do one more trajectory, or is that clear? Let's take a trajectory over here. The robot starts with its arm to the right, and its arm starts to come to the left, but doesn't cross the center line. Back, left, all the way to the right, shakes its arm back and forth, and eventually brings its arm back to center. Yes?
So in this figure, is the robot consistently missing?
Good question. So I've told you that sometimes the object is dropped above and to the left, sometimes it's dropped. You'll notice that all of these different trajectories have different shades of gray, which correspond to different initial angular positions of the objects. The objects are falling from different positions at the top of the screen, but I haven't told you yet where the object lands. But I have told you that the robot always ends with its fist pointing directly above it. Where do you think the objects tend to hit? Directly above, right? This is the most fit CTRN. This robot armed with this CTRN, no pun intended, usually catches the object. So the objects are falling from different initial horizontal positions, but all those objects are falling so that they hit right here, and every time the robot catches the object. What is the robot? We know a little bit about what it's doing. What is it thinking? How does it solve this problem? How does it know that the object is going to hit directly above it? When does it know that the object is going to hit directly above it?
I think when it hits directly above it.
Maybe. It doesn't look like it knows, does it? This robot is nuts. It's always waving its arm all over the place, except right at the end. There's a few cases in here. You'll notice these medium gray trajectories. Medium gray, we go back to our color bar here. That means that those initial angular positions of those objects was directly above. So these are objects that were falling straight down. These middle gray trajectories, they started at different positions, and the robot was doing this. And then during the last, about the last fifth of the simulation, it's waving its arm back and forth above it. Okay. So maybe it really doesn't know until the end. It's hard to say from this robot's perspective if this is an easy task or a hard task. This robot, in theory, could show off by just doing this. And that would be the robot saying, I know. I know long before the object ever gets to here, I know that that object is going to hit here. This robot, or this CCRN, certainly doesn't do that. So it's hard to say. Maybe it does know early on, and it's moving, but it already knows. The only thing that evolution cares about is that it grabs the object at the last time step, when the object hits that curved trajectory. There's nothing here in evolution that says put your arm where the object is going to hit long before the object ever hits there. So it's hard for us to say. There certainly is something that's common in all of these evaluations here. This CTRN causes the robot to do something. What is it? Doesn't always do exactly the same thing, but there's a general trend here. What's the general strategy for this CTRN?
Wiggle the arm a bunch.
Wiggle the arm a bunch, right? This thing is hardly ever still. Okay, so this plot makes that clear. What do you think that means?
I mean, if it's like trying to detect if there's an object somewhere above it, and it knows that there's this thing that is always above it, like if you wiggle your arm, like the infrared will blink off and on kind of, but if there's an object that's above that and it's still coming down at you, then it won't do that.
Exactly. This looks, once you digest this behavior, quote unquote, looks like what BabyBot did, right? I wave my arm It doesn't know there's an arm. I send an oscillatory signal to my motors, and I see a blob in my visual field do this, right? I send an oscillatory signal, and I've hit the apple, and the apple's rolling, and I stop moving, and the apple keeps rolling. There's some difference in the sensor-motor relationships I can cause. I can go like this, and I can watch my infrared sensors flick on and off. And then if I stop doing this, they stop flickering. But then there's something else that's causing my infrared sensors to change lengths at maybe a slower pace or a constant rate or who knows what, but it's different. It's likely, but again, it's hard to say from this, that this waving is part of the robot discriminating between self and non-self. You'll notice that in a lot of these cases here, when the object starts above and to the left of the robot, and the robot's little fist is torqued by the investigators to its left, there's occlusion. What's the first thing it does? Maybe it's evolved to unocclude the object, but then occlude it again. It's kind of odd. It may or may not be something you would do if you were in this situation. There's aspects of this evolved behavior that look familiar. Okay, this is me. I see some of you waving your hands, but I don't seem to have much control over that. That's the world. Looks like something we did, or maybe we did when we were little kids and we were trying to solve this problem. Yes?
Couldn't it also just be the fact that initially, when it's trying to learn to grab stuff, it's learning by moving around, and so it just kept that memory as like a way of getting to a final solution?
Maybe. This is one of the things that's fun about the minimal cognition experiments. The investigators leave it to the reader. It's not clear why. Maybe during evolution there clearly was a need to move because it has to capture the object at different positions relative to itself. So of course the robot has to evolve the ability to move, and the CTRNN is maybe just comfortable with continuously moving the arm. Who knows? Okay. Third one. Here we go. Another very, very clear building block of intelligence, at least for most folks. Memory, specifically short-term memory. If you can't remember what happened a millisecond ago, or a second ago, or 5 minutes ago, you're going to have a hard time in the real world. Someone who is smarter than you and can remember what did happen a millisecond ago, a second ago, 5 seconds ago, an hour ago, has probably got a competitive advantage over you. Intelligence tends to rely on memory. So how did they test this in the minimal cognition experiments? They went back to their Space Invaders robot that's going to move left and right along the bottom of the screen. So we have 2 motor neurons again in the CTRNN. Those 2 motor neurons are attached to 2 little rockets that can fire in opposite directions and cause the robot to move back and forth at various speeds along the bottom of the screen. They're going to drop a big circle from the top of the screen again. It might fall straight down, as is shown in this figure. It might fall at an angle. The single object can fall at different velocities at different angles. And all the robot has to do is move and be there when the object hits the ground. In this case, we're going to try and minimize d sub I, the horizontal distance between the object's final position. Where does the object hit the bottom of the screen at the end of the simulation? And where's the agent? The agent better have exactly the same horizontal position as the object. If it does, that's a d sub I of 0. Okay, that's what they're going to evolve the robot to do. We saw in the affordance experiment it can do that, but there's a twist in this case. You'll notice that the 7 proximity sensors in this case are drawn as dashed lines. What does that mean? It means that if the CTRNN keeps the robot immobile, neither of the rockets fire, the robot is still, then 7 values arrive at the 7 input neurons inside the CTRNN. The moment the robot starts to move, lights out. Those 7 input sensors no longer get input values. The robot goes blind. Okay. Imagine playing this game. We put you in a room and we drop objects from the top of the screen, and the moment you move, we put on some we put on some special glasses, that the moment the glasses feel you move, the glasses go dark. How do you solve this problem? How is the robot going to need to solve this problem?
Does it continue to be blind, or?
It continues to be blind. The moment it moves, it goes blind, and even if it stops again, good point, even if it stops again, it doesn't see. That's it. What would you do if you were learning to play this game?
One object at a time, or would it be more?
It's only one object, yeah. This problem's hard enough with one.
I think I would try and watch the object for, it'd be a balance, but as long as I can to kind of find its trajectory and then start moving. So you have to be really sure about where you're moving to.
Exactly, right? Think before you act. Generally speaking, humans tend to frown on other humans or other things that act and then think about what they did after the fact. We tend to think of that as not a very smart thing to do. This whole experiment is kind of designed around that premise, or maybe that bias that humans have. The wrong thing for this agent to do is the exact opposite of what you just said. Simulation starts and the robot moves. It's dead. That's it. All it would know, if it immediately moves, all it knows are the 7 proximity sensor values during the very first time step of the simulation. So it may know where the object is. The object is up there, but the minute it moves, it only knows position, or position of the object at t0, the first time step. It doesn't know which direction the object is falling at. It doesn't know about the speed at which the object is falling at. The only way it can know that is to observe the object, or at least observe changes in its proximity sensors at t1, the second time step, and maybe the third and the fourth, but don't wait too long, right? Humans also tend to look down on other humans or other things that think too much. I'm watching the object. Oh, I know where it's going to hit. It's going to hit by the door to the room in 3 time steps from now. It's too late. I'm not going to be able to get there. I know where it is, but I can't get there. So evolution is going to have to evolve the parameters that make up these C tier and Ns so that that C tier and N strikes the right balance for the robot. Think enough, but also leave enough time to act to solve the problem. Yeah? Okay. So where does memory come into all this? In all the lead up to this so far, I've deliberately not been saying anything about memory. Where does memory come in?
Maybe the robot can build memory about how long it takes for itself to move to where it needs to go.
Could be. That seems like a good piece of the puzzle, right? How long is it going to take me to get there? It's now 17 time steps before the end of the simulation, and I need to go over there. How am I going to do it? What else does this thing need to know or remember?
Memory about like previous positions of the object.
Previous positions of the object. I saw the object there at t0, and at t1, I now see it here, or at least my proximity sensors now have this value. Wow, that object is moving fast, and it's moving to the right. So in order for this thing to compute how this object is falling, it definitely needs memory. It cannot calculate velocity and direction of fall from a single time step. In many of the experiments we're going to see, it's not clear whether or not the robot is going to need memory. In this one, it definitely is going to need it. So far, so good? Okay. Like 2 times before now, evolution, 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 evolution. At the end, we get we have a population of evolved C tier and Ns. We pull out the C tier and N that's most fit, that has the best value of this whole thing here. Down here, they're again going to plot on the horizontal axis final object position. Where along the bottom of the screen does the object hit? Does the object hit at the bottom left of the screen, at the bottom center of the screen, at the bottom right of the screen? And in all of those conditions, what was the final position of the agent on the horizontal axis? It's a little confusing because this is the vertical axis here. So was the agent at the bottom left of the screen, bottom center of the screen, or bottom right of the screen? How does the robot do? How does the robot do armed with this most fit CTRNN? Pretty good. Optimal?
No.
Not optimal. Where is it having a problem?
Negative 40, 40, and 0.
Negative 40 at the extreme and positive 40, and then in the middle also. Again, hard to explain what's going on in the middle. The fact that it's having problems when the object hits very far, when the object hits bottom left and bottom right, may be easier to explain, maybe not.
We can assume that the robot always starts at 0, right?
The robot always starts at 0. The objects don't necessarily start at x equals 0. Above left, above center, above right.
Could it just be that it's like waiting too long? Like it's like by the time it like needs to get all the way to 40 or minus 40, it's just like too late. It can't get there in time.
It could be, right? Whatever's going on, when the object hits far to the left, the robot is not quite in the right position. Maybe it overshoots the object. Actually, it does overshoot. You'll notice the final agent position tends to be less than minus 40. It goes beyond.
And then like undershoots it.
What's that?
Like overshoots it and then undershoots it. Like at the farther distance.
Yes, you're right. Sometimes it undershoots, sometimes it overshoots. Thank you. I was wrong. Yep, same thing over here. So maybe, and again now we can start hypothesizing, it just waited too long. Could be. It always starts in the center. So in these cases out here, far to the left and far to the right, the robot just has further to travel. And remember, while it's traveling, it's blind, right? You know that the object is going to hit 3 centimeters in from the doorway. You now have to get over there with your eyes closed. Trickier, right? Or the object's going to hit about 6 centimeters to my right. That's a little bit easier for me to travel with my eyes closed. That's how it feels to us. Again, thinking about thinking is misleading. May or may not be the case for the robot. Okay, let's look in a little more detail about what this evolved CTRNN is causing the robot to do. Okay, horizontal axis is labeled with horizontal position. So this indicates horizontal position relative to the agent. So horizontal position of 0 is the agent has a horizontal distance of 0 relative to the object. It caught the object. You'll notice there's a whole bunch of trajectories here that these trajectories start top left, middle right, middle top. So going back to horizontal position, this is the object being dropped above and to the left of the robot, above and just a little bit to the left of the robot, dropped above and a little to the right of the robot, dropped above and to the right of the robot. Vertical axis here is labeled with vertical position. It's reporting the vertical position of the object. So again, time descends from the top to the bottom of this figure. You'll notice that all of these trajectories for a very short period of time are vertical. What does that mean? What is that telling you about the object and the robot? Yes?
It's just the time that the robot's only sensing.
It's only the robot is staying still, and the fact that the robot is staying still, horizontal position is not changing. These trajectories are a little bit vertical. The objects are falling straight down. They're dropped from different positions at the top of the screen, but in every case, they're dropped such that they fall straight down. Then, at some point in time, the trajectories become diagonal. What is that telling you? What does it mean when these trajectories go from being vertical to diagonal? The robot's moving. How is the robot moving?
Towards the object.
Towards the object. More detail.
Seems to move at a constant rate in all.
Yep. Okay, so in every case, it's the same C turn N, but the C turn N is receiving different sensory information in just these few time steps. It's watching the object, and then it starts to move. And in every case, you'll notice all the diagonal parts of all of these trajectories all have the same slope, which means the robot always moves at the same speed. It's very conservative, this robot. It always does the same thing. Never seems to be rushing or in a hurry. Constant movement. What does it mean that some of these trajectories have more vertical components than other trajectories?
The object is farther wide, the robot has less time to get there, and needs to take longer to get there, so it moves sooner.
So this CTRN seems to have hit on a reasonable strategy. If the object drops way to the right of you, you better start moving quickly. So the object starts falling straight down from over there, and within the first few time steps, the robot starts moving. And it's moving at a rate, if we follow this trajectory, it's moving at a rate that gets it almost to the object. But the object falls a little bit to the right of the robot. Almost got all the way there. The black lines, you can see they all converge more or less exactly at 0, so that's good behavior. The investigators painted some of these trajectories in gray to pull out or point out the few cases where the robot did particularly poorly. And as we saw already in this picture, this CTRN does particularly poorly for objects that begin falling near the center line or fall very far to the left or far to the right. Again, it's hard to explain why the robot has a hard time with these. My guess would be probably because this CTRN never saw exactly these conditions during evolution. What about this pair of trajectories over here or this pair of trajectories over here? Why do you think the robot has a harder time with these? If you were playing this game, why would you have a hard time with these?
Has to make the decision very quickly.
Why? Why does it need to make the decision quickly? It's got further to move. It moves at this rate that seems to get it just to the object in time. It's a little hard to see from this slope here, but this is telling us that the robot is moving at a steady rate. Is this the fastest the robot can travel? Remember, it's got these two motor neurons here that can push. Is this robot moving at this constant rate because this is the fastest it can go? You don't know unless you've actually read the paper, but you could probably guess from the fact that I'm asking you, this is not top speed. This is just the speed that this CTRN evolved to drive this robot at. This robot could actually go much faster.
I was just gonna say, it seems like it really likes to get to the ideal point right when it starts.
Yeah, again, it's a show off, right? It's like, I know where it's going to be, and I'm not going to rush. I'm not playing your games. I'll take my time, and I'll get there, and I'll be there just in time to catch the object. I'm really showing you, I know exactly where and when the object is going to hit. It's going at a relatively sedate speed. It could go faster. which means that the explanation for why it's doing poorly in these conditions is not because it had to start, because its top speed would only get it there in time. It's not the speed of the motors that's the problem here. Why do you think it's struggling with these extremal cases?
That's a question.
Yep.
What's the physics of the simulation like?
Minimal. There's not a lot of physics in here. No collision detection, no resolution. It's 2D.
Is there anything that like
What?
keep it going after it starts going?
There could be momentum. That doesn't really matter for our purposes. It could be that the rockets just fire and then shut off again and the robot coasts into position. Doesn't matter.
I have also a physics question.
Yep.
So, does this have inherently like knowledge of kinematics?
Ah, that's a great question. Does it have intrinsic knowledge of kinematics? So does it have knowledge of kinematics? Who knows? Like, is this C to an N integrating equations of motion?
Figuring out the acceleration due to gravity, like.
When you leave this classroom and your success in getting through that door is going to matter, is a function of your weight, your friction with the ground, momentum, other people in the room. Are you running the physics of motion as you get to the door? It's been a question in neuroscience for a very long time. What's going on in our heads? You might remember when we talked about Valentino Breitenberg, who dissects fruit fly brains. You all live in student housing, you know what fruit flies look like. They're super small. Fruit fly brains, super, super small. If Breitenberg were alive and if he were here, he'd say the fruit flies certainly don't have explicit knowledge of kinematics. They might have implicit knowledge. What does implicit knowledge mean? Let's go back to this for a moment. This robot never knows that there's a big black circle falling towards it. All it ever knows is my sensor values were this, and at the next time step, my sensor values were this. I predict at the next time step, my sensor values are going to be this. That's implicit knowledge. It doesn't directly know about the thing. It just knows how that thing, or whatever is out there, is impinging upon its sensorium.
But wouldn't it be more efficient to code in the kinematics equations when
Oh.
you're building the robot?
Okay, great question. Why don't we just give the robot knowledge of its world, right? Give it kinematics. Look at this room. What are we going to build into the robot? Do we tell it how many people are in here? Do we tell it the weight of all the chairs? Do the color of your shirts matter? How do we decide? In the old days, the answer was yes, we should put it in. The problem is, once you start, where do you stop? What knowledge of this room do you need to have, or does a robot need to have, in order to successfully get out the door? Hard to say, actually. So, since quite a while now, for decades, the assumption was going to be the robot will learn, or in our case, the robot will just evolve implicit knowledge of whatever it needs to know. And how do we know whether it's learned that implicit knowledge or not? It'll show us. Based on its behavior, we can conclude certain things. Some things we might not know. We know that in this particular case, the robot, quote unquote, knows where and when the object is going to hit. How it came to that knowledge is not clear. So, great question. Like, does it have implicit knowledge? Who knows? What exactly would that mean? It knows somehow about this falling object. But what form that knowledge takes in its head, unknown. Same goes for us, actually. Much is unknown about how you know when you see someone, whether you've seen that person before or not. You know, and you act as if you have, and usually when we check, it's true. You either have seen that person in the past or not, but what? What was going on in your head to make that determination? Unknown. Okay, these are good questions. Open questions in AI and robotics. Okay, back to our minimal agent here. Why is it having a hard time, do you think, with these two extremal cases? It's not speed of travel. It can move very fast, this agent. It could wait around for a long time and then chase down this object. think about the brain of this robot. It's being driven by a CTRNN with 7 input neurons that go dark the moment it starts moving. It's got 2 motor neurons that are controlling 2 rockets. Why might it be? Why? And then think about its brain. Look at the 2 rockets. Look at the distribution of the sensors. Why might this particular machine have a hard time when objects start falling from top left or start falling from top right? Go ahead.
Is it just the geometry, because the robot sensors are spread apart radially and the object is falling straight up and down?
Absolutely. In this cartoon here, if we dropped an object here, the robot would never see it. The geometry of the spread of the sensors. This is a physiological detail of the robot, so a detail about its body. This leftmost sensor would not hit this object over here. The only hope for this sensor to come into contact with this object would be for the robot to move to the left. But the moment it moves to the left, it goes blind. So by definition, if we dropped an object from here, it'll never see it. This robot does not have omnidirectional view. Neither do we, for that matter. There's limits to what it can do. These cases, the investigators dropped the object just at the edge of the sensor geometry. Those objects that are falling directly down, they connected with these sensors for just a few time steps and then whoosh, passed out of the robot's field of view. That's like if you were standing still and a bird flew out past the window. You'd see a flicker for a moment and then it's gone. Something passed through your peripheral view and maybe it matters. Was that a bird? Was that something else? Maybe you care about what that object was. You don't have much time to make that determination. Is it something you can safely ignore? Or maybe what you think you saw out the window suggests you should maybe leave the room? Who knows? You don't have much time to decide. This robot doesn't either, and it made a good guess, but it wasn't perfect. So you can sort of see in these 4 gray trajectories down here and where they land, the robot and the CTRNN are struggling at the limits of what the robot can do. Yeah? Okay. I'm going to skip over the next few of these. These will be optional for you. They're just more analysis of what we just talked about. We're a little behind where I'd like to be today. We got 3 minutes left, so I will just introduce the 4th and final and the funnest one of the 4 building blocks of cognition we're going to see in these experiments: selective attention. This is something that humans are very, very good at. I spring a quiz on you and you freak out, and then you see that the quiz is 3 weeks from now. You stop attending to it. You attend to it for a moment and then realize it's actually pretty far off in time. Then I tell you, I've changed my mind, it's now worth 50% of your grade. So now it's kind of an important thing, and yet it's 3 weeks off. So 50% of your grade in this class is going to be determined 3 weeks from now. And in one of your other classes, another fun-loving instructor springs another pop quiz on you and tells you there's going to be a pop quiz on Thursday, which is worth 10% of your grade. Which one do you study for? Which one do you choose to attend to? This is something that us and most other organisms have been struggling with for billions of years. Do you take the short-term reward or handle the imminent short-term punishment now? Or do you attend to the further off issue, which is more important, bigger stakes? It is a very difficult thing to do. The easiest thing is just put out whatever fire is closest to you. It's a pretty good strategy, but there's a better strategy, which is this fire actually won't kill me. I'm going to choose not to attend to it. I'm going to pay attention to that bonfire that's a little bit further off, but headed my way. We have a bunch of things that are impinging on our attention, and thanks to these things, you have many more things that are impinging on your attention all the time. And it takes energy. Literally, it takes energy to figure out what to attend to. So in this particular task here, they've got another robot that can move back and forth along the bottom of the screen. They're going to drop 2 objects. These objects are not attached. They can fall from different positions at the top of the screen, and they can fall in different directions at different speeds. At this point in time, you'll notice that this object is closer, but its dashed line is shorter than this dashed line, indicating that this object is falling more slowly than this object is falling. This object is falling faster, but it's further away. This object is closer, falling slower. You can probably guess what they're going to evolve this robot to do. Catch the object that hits the ground first, and then go and catch the second object when it hits the ground, wherever it hits the ground. In this cartoon, which object does the robot choose to attend to? Which one does it go after first? We'll see on Thursday. You have a quiz due tonight, and you're working on A7 or D2. See you then. Thank you.